have talked about all the reactions in chapter 10. So now we're going to put it together with synthesis. So as far as our synthetic strategies, this is just a summary of some of the reactions we've talked about. We can take our triple bond and we can completely hydrogenate it. But that's not usually very useful for synthesis because once we get here, we don't have any reactivity. So we can't really do anything else with it until we get to chapter 11, which will talk about radical reactions. But it's very limited into the reactions we can do. So typically this is going to be our final product. This is what we're doing. If we wanted to stop at a pi bond, which still has reactivity, we can use H2 or Lindlar's catalyst to get our cis. And for trans, we can use our sodium metal and ammonia liquid to get our trans. Then once we have those, we can still completely hydrogenate it because we know our double bonds can also be hydrogenated. But again, this final product is not very useful for synthesis, so usually that would be our final product. We have looked at taking a double bond and adding 2 additions of bromine, which is our halogenation. Once we have 2 bromines, and if we have 2 leaving groups, we can form a triple bond using our really strong base, NH2-. Now remember, this is different from our sodium metal and our liquid ammonia. This is Na plus NH2-, so that's a strong base with our sodium being our counter ion. Water has to be added second because if you add water at the same time as our base, water is just going to react with our base, and our base will not react with our compound. So water will not completely neutralize. It's still going to be a basic solution, but OH- is more stable than NH2-. So we'll form our hydroxide. We haven't learned how to take a single bond to form a double bond yet, but we will in chapter 11. Because again, there's not very reactivity in a completely saturated hydrocarbon because we don't have any functionality there. So we've talked about all of these reactions, and we've also talked about different reactions we can do with the triple bond and with the double bond. So when we're looking at synthesis, now the first thing we should do, because we have ways to form a new carbon-carbon bond, is to see the difference in our carbon skeleton. And it's also really helpful if you can locate the carbons in your starting material where they are in your final compound. Sometimes it's not as clear, but if there is a specific functional group or a specific branching that's not being used in the reaction, you can usually find it from your starting material to your final compound. So in this case, that tert-butyl group is pretty clearly in both our starting material and our final product. So we see this tert-butyl group, and we see it here. So it's pretty clear where our starting carbons came from. It's also very clear in this example that we absolutely have more carbons in our final product than we do in our starting material. And of course, if we have more carbons, then we have more hydrogens. But usually we discuss this in carbons. And it's also clear we have a new carbon-carbon bond. So it's very useful to be able to find that difference. So here is our 6 original carbons that we started with. And again, that tert-butyl group is fairly clear because you can see where it is in both our starting material and our final product. So numbering from there, we can see where our starting material carbons were. So we see our new bond is this one, because we didn't have that carbon-carbon bond before. And also notice we added more carbons to total 10 carbons when we only started with 6. So we added a total of 4 more carbons in our compound. So that means somewhere in our synthesis we must be adding 4 more carbons. And they must have this connectivity. And our new bond is between carbon 4 and carbon 7. That carbon-carbon bond was not present in our starting material. Now, at this point, we've only learned one way to form a new carbon-carbon bond. Otherwise, later on, we're going to learn other ways. But basically, to form a new carbon-carbon bond, we need a nucleophile, that's our carbon, so a carbon with a negative charge, that can act as a nucleophile and attack in an SN2 reaction. So the only way we've learned to do that so far is to form a triple bond and deprotonate it. Now remember, we cannot do this reaction through the double bond because as our double bond, that's not a very acidic hydrogen. That pKa of the hydrogen on our sp2 carbon is only about 40 something, and we don't have very many bases that's strong enough to deprotonate that. So we're not going to form that carbon nucleophile. And we need the lone pair on the carbon for it to act as a nucleophile because we need accessible electrons. So with this starting material, we don't have accessible electrons. The other big difference that we see is that we have a triple bond between carbons 3 and 4, where we didn't have that triple bond before. We started with a double bond. So that's a pretty good hint for you because that's the only route that we've learned to form a new carbon-carbon bond is through deprotonating a triple bond. But watch out because once I form a triple bond, I could convert it to a double bond. So always look for that. In this case, I did. Triple bond is retained. So the only transformation that we've learned to form a new carbon-carbon bond between carbons 4 and 7 is through deprotonation of a terminal triple bond. And we can do that. And we know how to take carbons, our starting material, to form a triple bond. We need 2 leaving groups, so that way we can form a triple bond. So we're starting to come up with our synthesis. So we can take a double bond and add 2 leaving groups to it. We've talked about ways to do that. And I just showed the main way we've talked about doing that, which is through the reaction of Br2 to form 2 bromines. So now we have 2 leaving groups, and we can form our terminal triple bond. Once we form our terminal triple bond, we can deprotonate it and have it act as a nucleophile. So that's our synthetic route. Again, you cannot do this through the double bond because that's not an acidic hydrogen. But the pKa of this hydrogen is around 25. That's absolutely low enough to deprotonate. Remember, in that reaction, we will retain our triple bond. So putting in our reagents, we can get to our Br2 compound by reacting Br2, and usually we use a non-nucleophilic solvent like carbon tetrachloride. And now we have our 2 leaving groups, and we have 2 beta hydrogens. This hydrogen's beta to this bromine, this hydrogen's beta to this bromine, so we can deprotonate those. And we can form our triple bond, but to do that we need our strong base. So excess N8 and H2, followed by water, will form our triple bond. Now once we have our triple bond, we can deprotonate it, making it a strong nucleophile. Then our carbon will have available electrons, and it can react. Now what's our limitation with this reaction as far as our electrophile is concerned? First off, what is our electrophile going to contain? What will the nucleophile react with? A partial positive charge. So, for a compound to have a partial positive charge, what will our electrophile contain? What kind of atoms? What kind of atoms react in an SN2 reaction? Our nucleophile reacts with what in an SN2 reaction? What would this compound contain? If a nucleophile is reacting in an SN2 reaction, what do we need for our electrophile to have? So how would our nucleophile react? What does a nucleophile do? If y'all don't speak up, I'm going to give you a test and stuff I haven't covered because we're having a test when it's located, whether we finish chapter 11 or not. So the longer it takes us to get through this, the less I might cover chapter 11. So we have a nucleophile. We We have a lone pair on a carbon has a negative charge. Is that stable? No. What will it react with? An electrophile. It doesn't really even need to be a strong electrophile. This is very reactive. Carbon is not very stabilizing. It's only somewhat stable because the orbital sharp. So, in an SN2 reaction, what does our electrophile look like? It's a molecule, contains carbons. What else? What do we need for an SN2 reaction to occur? Has to have a leaving group. That's all I was looking for. And what kind of atoms or leaving groups? Halogens. So we need a halogen-containing compound. Well, what's our limitation with this reaction? What kind of halogen do we need? How do we describe our compounds that contain halogens? What's our terminology to use? We have a halogen, it's attached to a carbon. How do we describe that carbon? It's partial positive, but how do we describe it? How do we describe the amount of R groups surrounding that halogen? Okay, so what's our limitation for our halogen-containing compound? Can it be tertiary? Why not? Too much stirred. SN2 reaction doesn't happen. If it is tertiary, what reaction would happen? Unlikely. We wouldn't form a positive charge under these conditions. Because remember, there's a strong base present, NH2-. We don't form a positive charge in the presence of a strong base. What other reaction can occur? E2. We don't want E2. That wouldn't form our product. E2 would just take our hydrocarbon, our halogen, and all E2 would do is form this compound. And in that case, what's our atom acting as? What's this acting as? Is it acting as a nucleophile? No, it's acting as a base. So that means we're reforming our terminal triple bond, but that's not what we want. We want a new bond. What about secondary? Would a secondary alkyl halide form our final product? Maybe some, but the major product would be E2. So what's our limitation? What does our alkyl halide have to be? Primary. Or methyl, but methyl is not usually that useful. And clearly it's not methyl because this isn't methyl. So later on, we're going to need to remember that because that's going to limit what type of reaction we're going to do. But is carbon-7 primary? Our alkyl halide is going to contain these 4 carbons. Where is our carbon-halogen bond going to be? On which carbon? 7, because why? Why does it have to be on carbon 7? That's where our new bond is. Our nucleophile is going to react with our carbon with the functional group on it. So, if it's not on carbon 7, we won't get that final product. In this case, this is very symmetric, so it wouldn't really matter, but later it will. So wherever your new bond is, that's where your leaving group must have been. Remember, SN2 does not go through a carbocation, so we don't have rearrangements. So carbon 7 is in fact primary, so we can do this reaction with it. So that's our compound. But before we react our triple bond with this compound, first we're going to have to add our strong base. Once we add our strong base and it's reacted and we form a negative charge, then we can throw this in. So that's what our structure should look like. And I have it written under there. And it doesn't really matter if your alkyl halide, here I have it drawn as chlorine, and then in my and then in this drawing that I already had in there, I have it drawn as iodine. Chlorine, iodine, they're both good leaving groups, so they're both fine. The main thing is we have a good leaving group. If we don't have a good leaving group, there's nothing for our nucleophile to react with, except for if we threw in water. Now, in all technicality, when we react this with this, if we use excess, remember we're going to form this. So instead of adding water, I could just then add this. But for clarity, when I'm explaining it to show that we're going through the triple bond, I broke it up into 2 steps. And you could to isolate this, but it's also okay to add just our excess NaNH2 to our compound that has our 2 leaving groups. That will form this, and then instead of adding water, you can add this. But if you add water, you're going to form that terminal alkyne, so then you have to deprotonate it once you've worked it up. So I'm showing it in 2 steps, so when you're looking back, you can be clear that I'm going through the triple bond. Now let's look at this case. The first thing we need to ask ourselves in this case is, and the first thing you should always ask yourself when you're looking at these, to try to figure out what your, and also just a note, this is showing you the mechanism. This is not isolatable, so I don't want to see this compound. You can doodle with it if it helps you, like for me explaining this, but this isn't isolatable. And in a synthesis, all of these steps have a separate mechanism. They typically will have a charged compound in the intermediate, but I only want you to draw isolatable compounds. So we can isolate this, we cannot isolate this. If we try to get this, it would just react with water in the atmosphere when we're trying to isolate it. So I don't want to see a charged compound as your intermediate products. These are products that you're isolating. If we look at this one, the first thing when you're looking at a synthesis, you should always look at is, do we have a difference in the amount of carbons from our starting material and our final product? Because they have to come from somewhere. If we have more carbons, we have to put them in. They're not just going to happen. So that's the first thing to look for. And again, numbering and highlighting can help. Also, like I said, this won't always work, but it's really useful to figure out where the carbons from your starting material are in your final product. So looking for substituents or a specific branching that's really clear from your starting material to your product will help you with that. You can only have reactivity or only have reactions on carbons that have reactivity. So for example, if we're looking at this carbon, there's no reactivity here. So unless if we put reactivity there through a reaction, nothing's going to happen at that carbon. We only have carbons and hydrogens. We don't have any partial positive charge. We don't have any available electrons. We don't have any partial negative charge. We don't have any lone pairs. So we don't have any reactivity. Our reactivity is where our triple bond is. So looking at this, the question is, do we have more carbons? This one might not be as clear as the other one, but if you number them, then you will clearly see that we started out with 5 total carbons. And if I draw those same, and again, that isopropyl branching is pretty clear. That's the only place you have branching is here. So it's pretty clear where our carbons are. So we see we did add a new carbon-carbon bond. We added 2 new carbons, carbons 6 and 7, and we formed a new carbon-carbon bond between carbons 4 and 6. The other thing to notice is we don't still have our triple bond, so we must have reacted it after we formed our new carbon-carbon bond. Why do I know that we reacted it after we formed the new carbon-carbon bond? How do I know that? The only way we've learned so far form a new carbon-carbon bond is through deprotonation of a terminal triple bond. If we don't have the triple bond, we can't deprotonate it. So I must have reacted the triple bond first. The next thing to note, do we have any pi bonds in my final product? But we started with a triple bond. So when we did this addition, which we know we can do our Br2 followed in the presence of water, so that'll form our OH and Br. But did we do that reaction with a double bond or a triple bond? So if we had a triple bond and we reacted it with Br2 and H2O, will we form this product? You shook your head no. Why? How many pi bonds are in a triple bond? So how many times can it do an addition reaction? So if I add one equivalent of Br2, how many times will that add? But what will be left over? If it adds once, because I have one equivalent, what will be left over? A pi bond. It could also add twice. Did we add Br2 and OH to a pi bond once or twice? Once, because how many bromines, how many OHs do we have? Do we still have a double bond? I mean, a pi bond. So does that mean we started with a triple bond or a double bond? We had to have started with a double bond. If we only did one addition and we started with a triple bond, we would still have the pi bond present. We don't have the pi bond present, so once we formed our new carbon-carbon bond, then we must reduce the triple bond to a double bond. Because if we don't, and we only do one addition, we'll still have a double bond present. The next thing is, this one's, the stereochemistry is specified, so we have to consider it. And notice that it is anti-addition, the way that our carbons are drawn, so that must mean in this case we started with a cis double bond. Because remember, our Br2 forms our bromonium ion. So once we form this, we have our water present. It's going to attack. It has to attack on the backside because this is blocking it. If we started with a cis double bond, this is what our product would look like if I draw our carbons in exactly the same place. If we start with a trans double bond, I still get anti, but notice how it's drawn. I'm drawn with my two R groups in the same side. I can rotate. What's that going to do to my stereochemistry? Nothing. When I rotate, it doesn't change my stereochemistry. But if I rotate, if the OH was coming forward, and I rotate that bond, now how do I draw it? I'm drawing it to the back. I haven't changed it. If I assign this R and S, it's still going to be the same assignment. So notice that it looks like it's cis, but it didn't add cis. It added trans. Because remember, single bonds can freely rotate. So based on the fact that this one is anti here, we must have started with it's cis because we're not showing that rotation. It can still rotate, but that's not the way it's shown. So we have a couple of things we're looking at for this one. So we know we're starting with a double bond. We know we're starting with a cis double bond. We know we're doing the double bond because we only have one addition of Br on one carbon, OH on the other. So that means we don't have a pi bond left. So we must be starting with a double bond. We're starting with cis because our final product is cis. Now there is a problem with this particular compound. And the problem is, with this particular compound, that we don't have any regioselectivity. So I'm drawing this with the OH in carbon 3 and the Br in carbon 4. Realize you will have two other minor products that through this route we can't control. Not by the way we're doing this particular reaction, where our Br is on carbon 3 and our OH is on carbon 4. And as of what we know now, we don't have a better route to avoid this. Later on, we'll learn other routes that we won't go through the triple bond, so we might not have this problem of regioselectivity. But right now, based on the route we have, realize that these two compounds can only be at 25% yield each, because we do have our two other possibilities, and we don't have any selectivity to stop that. And sometimes that's the case in organic synthesis. Sometimes there isn't a good route to give you the best yield, or a high yield. Which is why you'll see a paper where an overall synthesis might only give you an overall 5% yield. And for that particular reaction, that's good. So 100% yield is what you're trying to get, but it's really unlikely, and sometimes there are limitations. So based on what we know, there's no better route for this at this moment. We don't have any more or less substituted carbon. We also know we have to form our new carbon-carbon bond through our triple bond, because if we form our double bond first, we can't deprotonate that hydrogen. We can only deprotonate that hydrogen on a triple bond because it's a lower pKa. And sp2 hydrogen pKa is 44. This pKa is 25, so that we can deprotonate. So, putting in our reagents, we're going to deprotonate our terminal triple bond. Our triple bond's already there, so we don't have to do anything with it. It's good. It's ready to be deprotonated. And we're adding carbon 6 and 7. Those are our new carbons. And in this case, just for clarity, our new bond is going to be between our carbon 4 and our carbon 6. That's a 1. Because carbon 4 is the one that's going to be having our lone pair, and carbon 6 is our partial positive charge, so that's where it's going to attack, because it contains our leaving group. And in this case, it's showing iodine, but you can show chlorine or bromine, any of our good things. That forms our new carbon-carbon bond between carbon 4 and carbon 6. So we're good there. Remember, the amount of carbons in our final product has to come from somewhere. So if you didn't add it in, where would it come from? So total, we have 5. We're adding in 2. So our total amount of carbons should be 7. So you can always double check yourself there. I have 1, 2, 3, 4, 5, 6, 7. That makes sense. I started with 5. I added 2. So watch your amount of carbons, number them, highlight your new bond. You can read all that. I don't mind you using a highlighter on your quizzes or tests. I want you to be able to see it. So do that, practice with that. So now I've done that. I have my new carbon-carbon bond. I have my carbon backbone. But I need to reduce this to this by adding 2 hydrogens. We know we can't use H2 and palladium because that would form only our single bond, and that won't be reactive. So instead, to form our cis, which reagents do we need? Lindlar's catalyst, we do need H2 still. We need a source of hydrogen. But in this case, it's H2 and Lindlar's catalyst to form our cis. Our trans, the hydrogens are coming from our liquid ammonia. But for Lindlar's catalyst, that's still going to be a palladium, but it just has R groups that blocks that second addition from happening. So it blocks the catalyzation of the second addition. Now our last step, we are adding bromine and OH to our pi bond, so that would be Br2 in the presence of water. Again, we do have a limitation where the final product shows where OH and Br regiochemistry is, but we don't have any selectivity. Neither carbon is more or less substituted. So we do have a small problem in that case, but it's just a limitation, and based on what we know, we can't really fix that. Not yet. Later on we'll be able to, and we'll find better routes. So looking at this case, this one is one where it might not be as clear where our starting carbons are, because we don't have any function, we don't have any substituents or branching occurring. But we do know one thing, and what's that one thing? What can you clearly tell me about this reaction? We clearly have more carbons in the product. And in this case, because it's just a linear compound, there's no branching at all, we'll just assume that these 1, 2, 3, 4, 5 carbons are the first 5 carbons. Because it could be these, but let's just stay consistent because we don't really have any reason not to be. There's no branching anywhere. So the question is, how many more carbons did we add? And again, numbering can really help, especially when you have a long chain. It's a little bit harder to see. So numbering can help you from making a mistake, keep you from making a mistake. So there's our original 5 carbons. So we have a total of 9 carbons, so that means we added 5. And where's our new bond? Between which 2 carbons? 5 and 6. So again, the only way we learned how to form a new carbon-carbon bond is through forming a triple bond and deprotonating. So can we take this compound and form a triple bond? Yes, it has 2 leaving groups. It has a hydrogen on both carbons 4 and 5, so we can deprotonate those. We can form our triple bond. Which reagent do we need to do that? It's listed there. We need A. B is not strong enough. The pKa of our alcohol is 16. The pKa of our triple bond hydrogen is 25. Remember, the lower pKa pushes the reaction in that direction. So that means that this is not strong enough to deprotonate our triple bond. That oxygen with a negative charge is more stable than a carbon triple bond with a negative charge. So we need our stronger one, which is A. B wouldn't work. Not for this case. So A will, if we use excess, will form our triple bond and it'll all the way deprotonate. So once it deprotonates, we have our triple bond. And we can add our extra carbons there. And remember, we added our excess NH2 minus, so we can deprotonate all the way here. We're not really isolating it completely. So again, how many carbons are we adding? 4. So which of our alkyl halides are we using? Butyl chloride, because we're adding 4. So remember, that just means we have 4 carbons with in this case, we're using chlorine. So that's our 6, 7, 8, and 9. Now remember, what compound is that? Are we going to have any pi bonds after we react our strong base with our alkyl halide? Yes, we still have a triple bond. Our strong base just deprotonates our carbon, and that attacks, but we don't do anything with the pi bonds. If the pi bonds weren't there, we couldn't deprotonate our carbon. It wouldn't be acidic enough. So after this step, we still have our triple bond. I just numbered 2 carbons and 2 numbers. Okay, 8, 9. So now we have our total amount of carbons. We have 10. I'm sorry, 9. I just numbered them. We have 9. That's how many we have in our final product. But we still have our triple bond. So which reducing agent can we use to get from here to here? We can use our H2 and our platinum, palladium, or nickel. In this case, we have platinum being shown, but it doesn't really matter. Because we are fully reducing it, because notice there's no pi bonds between 4 and 5, but we definitely have our pi bond, our triple bonds between 4 and 5. So which of our answers then? We have A and then G and then our E for H2 and platinum. Again, when you're drawing these, of course, with the questions, I can't really have the full steps for each one. So you're just putting in your reagents. But what I want to see is your reagent and then the resulting isolatable compound. That way I can fully see if you're understanding it. So in these multiple choice, I suggest, and especially there's a couple in the homework that are multiple choice like this, I suggest working them out, drawing your isolatable compounds, and then choosing your reagent like I just did here. Also, again, this is where the second edition solutions manual is much better than the first edition, because the second edition solutions manual just lists the reagents. I mean the first edition. The second edition actually shows the reagents and which compound forms after you react. You should never just list the reagents. You really should be thinking, if I reacted with these reagents, which compound would I form? That'll really help you. Some people, there are definitely organic chemists out there, there are definitely students that get it really quickly and they can see what each step forms. But that's not common. I can't do it. I have to draw it. I can't skip drawing a step. So don't skip drawing a step. Don't try to do it faster. Just be clear and then you won't make mistakes. So let's look at the next iClicker example. So here, the first question is, do we have the same total number of carbons? Because clearly we have two compounds. So we started out with how many carbons, and then we ended up with how many carbons. So in this case, we started with 6 carbons. And this is one of these cases where the substituent, carbon 6, is pretty clear where it is in our starting material and our final product. So use that. So clearly this is carbon 6 because we have that branching. So based on the fact that in my starting material carbon 6 was attached to carbon 3, that's probably still likely. So that's based on my numbering. So now I can clearly see where carbons 1, 2, 3, 4, and what I labeled as 6 was. Notice what happened. What did we do? We broke the bond between carbons 4 and 5. And we broke the bond between carbons 4 and 5 by forming a carbon-oxygen double bond and another carbon-oxygen double bond. What reaction did we talk about that does that? Oh, ozonolysis. Ozonation, yeah, but it's ozonolysis. But that's where you're going. So, reacting with our O3. Now, that means that our pi bond for ozonolysis has to be between which two carbons? To break the bond between 4 and 5 through ozonolysis, what does ozonolysis react with? What does our ozone react with? What functional group? What was this whole chapter reacting with? A double bond, a pi bond. So the pi bond has to be between which two carbons? 4 and 5. Because it's breaking the bond between 4 and 5. We're starting with it between 3 and 4. But we're breaking the bond between 4 and 5. So that means we have to do what? Rearrange the functionality to be between 4 and 5. The next thing, though, we have our pi bond is between 4 and 5. I want you to think about is, did we break a double bond or a triple bond in ozonolysis? What's the difference between our final products? If we take ozonolysis and react it with a double bond, what do we form? How many additions do we have with a pi bond? That's a double bond. How many? If we have a double bond, how many pi bonds do we have? 1. So how many additions of ozonolysis can we have? So how many alcohols are we going to have in both products? Or oxygens. Let me not say alcohols. We don't have any alcohols. If we started with a triple bond, how many additions can we do? So what do our products look like? It's 2 oxygens. So it forms what functional group? Carboxylic acid. Our aceto-guano-hexane OH. With the exception of CO2 if it breaks the terminal alcohol. So, did we form carboxylic acids? No. So we must have broken a double bond or a triple bond? A double bond. So we know we did ozonolysis, that's pretty clear because we broke apart the molecule, and that's the only reaction we talked about that really breaks the bond. So just to be sure, we want to make sure whether we're doing ozonolysis with a double bond or a triple bond. If we form CO2 in carboxylic acids, that's a triple bond, but here we're not, we're forming an aldehyde and another aldehyde. So that means that we use double bond. We only have one alcohol, oxygen in our final products. So we know we need our double bond between 4 and 5. How can we do that? What would be our first step? We can do an addition. What can we add? And where is the bromine adding? On which carbon? Carbon 4. So if we add on carbon 4, what do we need besides just HBr? Peroxide, because that's what? Xantime or Markovnikov. We added our bromine to our least substituted. We need it on carbon 4 because if it's not on carbon 4, our beta carbon can't be carbon 5. We need our beta carbon to be on carbon 5 so we can form a double bond between carbons 4 and 5. So now we can form our double bond. Is our double bond our most or least substituted? Least. So what base do we need? A large, strong base. That forms our double bond between 4 and 5. Technically, this synthesis we could have done in chapter 9. And then our last step is, of course, our ozonolysis. Now we have our double bond between carbon 4 and 5. So here our answer is we have to add E first. That forms compound 1. And then we add C. The potassium is our counter ion. That would work just as well as sodium terbutoxide. That's just our counter ion. To form compound 2. And then our last step is our ozonolysis. So that's E, C, and D. Again, when you're going through these, write down your mark and then choose your ones. Because on your exams, your quizzes, you won't have multiple choice. So you'll just be showing me this. And I say it's easier to figure it out and then look at your choices than to look at your choices most of the time. Again, I'm going to be going through synthesis today at 12:30. So we're going to be going through the chapter 11 that's on Moodle. Now we're going to start with radical reactions. That's going to be chapter 11. In this chapter, we're going to really look into this mechanism, but we're going to do that at the end of the chapter. Before we get there, we're first going to talk about radicals. So our radical So what is a radical? What does it look like? So first off, a little review. Remember, bonds can break in two ways. We can have homolytic bond cleavage. First off, how many electrons are in a single bond? 2. Every covalent bond has 2 electrons. So bonds can break homolytically to form radicals, where each atom that was participating in the covalent bond takes one of the electrons. Or we can have our heterolytic bond cleavage, where our most electronegative atom typically takes our electrons. That's mostly the reactions we've been looking at when we form ions. But in this chapter, we're going to focus on this reaction. So the big thing to remember here, especially when we're going to start looking at our mechanisms, is that we're just breaking that every bond has 2 electrons. So we have to account for every electron. So our free radicals form when a bonds break homolytically, and we have an uneven paired electron. So we have an electron that's not participating in a pair. Also, and we'll talk about this in a little bit more detail when we talk about the mechanism, but we typically show the movement of 2 electrons with this double-headed arrow. But for this chapter, we're going to be showing the movement of the electrons with a single barbed arrow, which represents 1 electron moving. So just a little bit about our free radicals. If we look at our charged particles, our carbon that has a charge is sp2 hybridized. Our carbocation is trigonoplanar. Our carbanion is sp3 hybridized, and it's trigonopyramidal because those lone pairs take up more space to push the R groups closer together in a pyramid-like shape. So what does the radical look like? The radical has 1 non-bonding electrons. So experiments have shown that it can either be thought of as this trigonoplanar, but instead of having an empty p orbital, it has an electron in it, or a really shallow pyramid, because the 1 electron is repelling the other atoms because it's not paired, so it's not stable. But it doesn't have a charge, it only has 1 electron, so it doesn't push away as much as this one does. In this particular chapter, we'll be thinking about it more like this, because this is rapidly linear converting, so the average of this pointing down and this pointing up is this. Which is more true? That's a bit above where we are in this class to go through. If you take advanced organic chemistry, if you're a chemistry major, you may spend more time with this concept. But a description at any average time, depending on what else is attached, we can usually think about it in the trigonoplanar way, because this is happening so fast that the average is being trigonoplanar. Because it's not nearly as trigonopyramidal as here, because we have 2 electrons pushing away. Here we only have 1. So we're going to mostly think about it as trigonoplanar and not as the shallow pyramid that interconverts rapidly, only for to make it simpler for us. But in reality, it's a little bit more complicated, but above this class. This is more of an introductory organic chemistry class, not a real organic chemistry class. So if we're looking at this, we can think about it as our trigonoplanar. As far as stability, notice that when I showed that, free radicals don't have a formal charge. But it's still not stable, because our electrons want to be paired, and also, if carbon has a free radical, how many electrons does carbon have? Let's look back at it. We have 2, 4, 6, 7. So we don't have a complete octet when we have a radical. So even though we don't have a charge, it's still unstable because we don't have a complete octet. And remember, our electron is negative. So in the same way that carbocations can be stabilized, oftentimes our radicals can be stabilized the same way, because our atom, even though it doesn't have a formal charge of a positive, it still wants another electron, so it'll be stabilized by groups that push more electron density towards it, because it wants that octet. So the more electron density being pushed towards it, the more it feels like it has an octet, even though it doesn't. So our stability is exactly like our, well, we won't say exactly because these are more stable than carbocations, but as far as our trends, the trends are the same as carbocations. Because R groups are electron donating through induction, the more carbon groups we have, the more stable. So methyl radicals aren't very stable, primary are more stable, secondary even more, tertiary are the most stable radicals that aren't being stabilized by other things like resonance. So we see the same type of stability as for carbocations, and that makes sense because the more R groups, the more electron donating through induction. And just like a carbocation wants more electrons, our radical wants to have 8. It only has 7, so it wants more electron density. So pretty straightforward there. When we are looking at these reactions, we're going to be starting with neutral compounds, and we're going to be removing a hydrogen to form a carbon radical. So what we can look at is our bond dissociation energy. Remember, our bond dissociation energy is homolytically cleaving our bond to form 2 radicals. So the lower the bond dissociation energy, the easier that carbon-hydrogen bond is to break homolytically to form radicals. So what we can look at is our resulting carbocation. Radical. The more stable the radical, the easier that bond is going to be to break. The less stable the radical, the less likely that bond is going to be to break. So looking at bond dissociation energies, the lower the bond dissociation energy, the easier that bond's going to be to break. These are all starting at the same energy. So what we're looking at is if the radical is more stable that results, then it's going to be easier to break that bond, so a lower energy. So what we see is, in agreement, if we know that a more substituted radical is more stable, it makes sense that that would have our lowest bond dissociation energy. That hydrogen would be the easiest carbon-hydrogen bond to break. Because we have the lowest bond dissociation, we have the most stable radical present. So we'll often be talking about this in bond dissociation energies. And in this chapter, this is going to be important because we're going to start with a neutral compound and we're going to try to form radicals. So we're going to talk about what's the most likely place for a radical to form. And we're going to be considering this. What's our most stable radical? I'm going to stop there. And we're going to start looking at mechanisms for radicals. So read ahead about radical mechanisms. Because again, it's not a lot different, but we are talking about moving one electron at a time. So it's slightly different. And we're going to talk about resonance as well. Have a good weekend. Remember today, 12:30. You too.